We'll see if this is gonna be cool. Um, so what is this course is about? So this course is about the theory behind linear regression. Um, and so the most like fundamental tool is statistics, you could say. And then you hopefully have seen regression somewhere, like 100A, 100B. How many people have seen regression before? Okay, in what course? Most likely not 100A. Are you saying 100B or something like that? This is what Cloud wrote, which is probably wrong. Yes. 101A. 101A, okay. So that's close. So you've seen it. Have you seen it in 100B? No. Anyone else has seen it outside 100A? Yes. 100B. Okay, so you have seen it in 100B. Okay. So that's a good place to see. So this is about the theory of regression. I'm assuming you said 101A. So it's not about the theory, right? But you know how to do the like application. Applications, okay. And you do the coding. Yeah. Okay. So you know hopefully about the application and you know how to code. Thank you. So this is the idea is we want to teach you what is behind the scenes and a little bit more rigorously. And for that you need to know about linear algebra and probability. And it's a fun course if you want to understand what is regression about. And it's also a fun course to learn about linear algebra in practice, and a little bit about probability. And if you do good in this course, you learn a lot about the intersection of probability, like linear algebra and statistics. And one of the most fundamental tools in statistics. Okay. So what is the key insight in this course? I wish I had able to like just let it scroll. So the key insight is fitting a linear model is projecting onto a vector like subspace, or like projecting a vector like is exactly projecting a vector onto a subspace, a linear subspace. Okay. So this side is the statistics, this side is linear algebra. Okay. There's a link between another complication. So a link between statistics and linear algebra. And so how do you go like have it like an understanding of what this sentence means, like this one? So what is projecting out the vector space? Has anyone like seen it in? Yeah, okay, so you've seen it in linear algebra? Yeah, it's a point. Okay. How many people have seen it in linear algebra projection? Okay, good. Okay. The subset of people have seen it. Okay. So we're gonna have an easier time. So almost everything, like estimation, inference, diagnostics, they all follow from this geometric page. And so let's move on to these points. So then why you start with linear algebra, that's the reason. So I'm going to spend some time just reviewing linear algebra. So hopefully most of the material you've seen, you start about like with subspaces and then bases and stuff, and then projections and a little bit about spectral decompositions, which my guess is that not many people maybe have seen or spent some time with. They're very useful. And we're going to need them a little bit in the course, but not too much. So most likely we'll spend the first 3 lectures reviewing and building this toolkit. It's a little bit too much, but I find I can't do it any other way. I like to talk about linear algebra because it's going to be, hey, this course is heavy on linear algebra. So if you keep pace, then hopefully you're going to be fine. And so we're going to do, today is going to be linear dependence, span, basis, dimension, column subspace, column space, and rank of a matrix. The next lecture is about inner product, orthogonality, orthogonal complement, norm, and projection. The lecture 3 is spectral decomposition, of symmetric matrices and plotted the limit of each other, more or less. So the goal is to build the tools to understand this statement. Basis for destination is equal to projection onto the common space of X matrix. Okay, that's roughly the content of the course, plus the consequences for statistics from like probability study. Any questions so far? So far, so good. Okay. So let's move on to the topic of today's lecture. So we're going to start with linear independence. Right. So you say like a set of vectors are linearly independent if a non-trivial linear combination then is, sorry, you say that they're dependent, linearly dependent if a non-trivial linear, so if this holds, let's see. If a non-trivial linear combination, okay, here is non-trivial, is zero. So what is a non-trivial linear combination? What is a non-trivial linear combination? What is a linear combination of vectors? What is a vector? Yeah, okay.
It's multiplying all of them by a constant.
Yes. Okay. So we have a bunch of vectors. I'm going to assume that you know what a vector is. Okay. And then you multiply each one by a number, by a scalar, and then you add them up. So something like this. So CI's are here, numbers, and then XI's are vectors. Some people write it with boldface or like with some arrows like this, but I'm not going to do that. Just you have to like understand from the context what is a vector and what is a scalar. Here CI's are scalars, XN's are XI's are vectors, and this notation is just, hopefully people know, this is just C1 x1 plus C2 x2 plus Cn xn. So if you don't know this notation, you're going to have a hard time in this course. Hopefully everyone knows. So the things that I try to not emphasize, hopefully, but if you don't, like let me know if anything is unclear. Let me know. So this is a linear combination. And the idea is that a linear combination is equal to zero. So what does the non-trivial part mean? Yes.
Not all the coefficients are zero.
Yes, not all the coefficients are zero. So if all the coefficients are zero, this is trivially true. So that's not a property that we want to focus on. So we want a linear combination, at least one of the coefficients is non-zero. So if that happens, then the set would be linearly dependent. If that can't happen, so there is no non-trivial linear combination that is equal to zero, then there's independent. So you define linear dependent or linear dependence, and then the opposite is linearly independent. So how many people have seen this before? Okay, good. Now we can answer this question. So which of these two sets of vectors are linearly independent? So it's a property of sets of vectors. So we have three vectors in R3. And the question is that which of them, if any, is linearly independent? Anyone? Yes.
The second there, or second question.
The second is linearly independent.
Right.
Why?
Well, I just look at the third dimension at -1, it's never going to get carried.
Okay, so that's good. So -1 is not going to be zero. Okay. What's that?
Correct. There's nothing to balance it out.
Yes,
Or to
yes.
cancel.
Okay, so but that's not going to be enough. So if I set something like this equal to zero, then I get a bunch of equations. The third one would be negative C3 is equal to 0. So this implies that C3 is equal to 0. C3 has to be 0, otherwise it can't happen. But the way to show it is that you set it equal to 0 and see if you can either find a combination which is non-zero or just prove that all the coefficients are 0. The C3 has to be 0. But what about this B3? They can balance each out. So if I write the other two, you'd get this. C1 minus C2 is equal to 0. Okay? Yeah.
So from the second one, C1 is equal to C2, and if you use that for the first equation, you will get 2C1 equals 0. So then C1 is 0 and then C2 is 0.
Yes. So from the second one, C1 is equal to C2, and then you plug in, and basically you solve your set of equations. The only solution is 0. So this proves that you pick a general linear combination, you say equal to 0, and you prove that they have to be all 0. So they can't be, any one of them can't be non-zero, so this set has to be linearly independent. How about this one? Yes, okay, so one, yeah.
You can set C1 to 2 and then C3 to -1.
2 times this, plus let's say 0 times this, plus
-1.
or minus 1 times this is equal to 0. So basically this is twice this one. If the multiply is by 2, subtract this, is 0. Okay, to see one of them is a scale multiply, the others, like one other one, and this would be linearly dependent. Okay, linearly dependent. Okay. Sounds good. So for linear independence, you have to prove you show that there is no coefficient. For linear dependence, you have to show like an example. Sounds good? I'm not going to spend too much time because we have a lot of things to do, but if it's not clear, let me know. This is the basic building block of kind of linear algebra. A bunch of exercises. If you have a bunch of pairwise orthogonal vectors, they're going to be linearly independent if they're non-zero. So orthogonal we'll see. But if you pick any two and they're orthogonal, then you can prove it using that idea that you set a linear combination to 0 and then prove that the coefficients are 0. That's one fact. So a set of vectors that contains a 0 is going to be linearly dependent. This is really easy to show as well from the definition. Okay, questions? So we're going to move fast. So what is a span of a set of vectors? So we have a set of vectors. We define something called a span. It's the set of all linear combinations of them. Okay, so you take a bunch of coefficients, you form the linear combinations of I from 1 to NCI xi, and then you let the coefficients vary. So this notation means the set of all linear combinations as C1 up to Cn varying R. All the possible linear. So this defines a set of vectors. And see what we can say about it. For example, if I have this set, 1, 1, 0, and then 2, 2, 0. I can form a general linear combination. The coefficients are like, these are dummy variables. I can name them T1 times the first vector plus T2 times the second vector. And then if you do a little algebra, this is really T1, T1, 0. Hopefully this is clear. Plus 2T1, 2T2, 0, and then you add them up, you get T1 plus 2T1, T2. 2T2 and then T1 plus 2T2 times 0. And then I can just factor out T1 plus 2T2 is the same. So it's as if I write this times 1, 1, and 0. Okay. And then I vary T1 and T2. And then I'll let you think about this for yourself. As I vary T1 and T2, it's as if I just have a general T. Yeah, I get all the multiples of that thing. Okay. So this is this set. Hopefully this is easy to see, and this is, just think a little bit about it. Okay, anything that I can find in R, I can write in this form. Let's say I can take T2 equals 0 and T1 T. But then anything like this, I can write it like that. Just keep finding T. So there's a one-to-one correspondence between these two sets. And so we get something like this. So is that kind of clear? So this is a version of like writing the span of these. So what does this set look like? You want? Yes.
A line of like,
Yes. So this is just going to be a line. It's just going to be the same. It turns out that I can write it as just the span of 1, 1, 0. By definition, if I just run like same definition on this, as this is because there's just one word. So the span of these two vectors, same as the span of this one. And this is just defining a line. The span of a single vector is a line. It's everything that's scale multiple of this. So if you have the x, y, z axis, let's say, and the first coordinate is x, the second is y, the third is z, then this vector is going to be like 1, 1, and then 0 here. So that's 1, 1, 0, let's say. And then when I scale it up, so this multiplied by 2, multiplied by -1, and it just spans this entire line, which is in the xy plane. So the span of this is the line, right? And it's the same as the span of these. So you can see somehow this is more compact. In some sense, it's better that this is done. So I can write the span of a bunch of set of vectors as maybe the span of a smaller subset, maybe. So far, so good. That's the span. It's a so-called linear subspace always. So anyway, so you can do another exercise. In the interest of time, I'm gonna let you work it out. So if you start doing this with those two vectors, you do T1, T2, and then you simplify to this. This I can't pull out the two. So T1 plus T2 and T1 plus minus T2 can take any two values. So the easiest way to see is that if you let this, for example, be alpha, and this be beta, for any alpha and beta, I can solve for T1 and T2. Okay. For any alpha and beta, there is a T1 and T2, and so this set is going to be like alpha, beta, 0. So what does this set look like? A set of all vectors that look like this as alpha and beta values.
Like all of R2.
All of R2, it's like, okay, so this is in R3. It looks like R2, but it's like the XY plane. So it would be the entire, this plane. Right, because anything there I can get. So anything here I can get. By this operation, nothing outside this plane. And I can pull alpha and beta out, I can write it like this. The same, and then you can see that this is a linear combination, general linear combination of these two vectors. So it's really these two vectors. Okay, this is an example where we started from two vectors and then we ended up with two vectors. And it turns out that I can't write this subspace, it's called the subspace, as a span of a single vector. I just always need two vectors. These are a little more simple. These are like standard basis vectors, but they span the same thing as those vectors. So we can have like a span that needs two vectors to generate. Does this kind of make sense? You go think something like this. Okay. What is this number? Like, what is that? So are these vectors independent? Linear independent. So how about the previous case? Are these linear independent? No, they're not linear. But how about this set? Is this set of vectors linear independent? A single non-zero vector is going to be a linear independent set. Yes. I mean, it's not really like from a definition, it works because if you C1 times this equal to 0, it has to be C1 has to be 0. So here we have two linearly independent vectors, and it turns out that you need two linearly independent vectors. You can't do it with a single linear independent vector. Okay, this number has a name, kind of. Anyone knows the name? Yes.
Dimension.
Dimension. So that's the dimension of the space. So this is kind of the idea behind like a basis and dimension. So any questions before like you formally define it? So what is a basis? What is dimension? A set of linearly independent vectors that spans the subspace is called a basis for the subspace. So here we have a set of linearly independent vectors, either this one or this one, both are linearly independent, and they span xy plane, so they're a basis for the xy plane. Okay. Here we have a set of vectors that span this line, but they're not linearly independent. So this is not a basis. This spans the line, and then it is linearly independent. So this forms a basis. But you have a basis with single element. Okay, so the idea of a basis is that it spans the set or a subspace. I'm not formally defining what a subspace is, but you get like a sense of what a subspace is. I hope you know what linear subspaces are. If you don't know, just review. Informally, you get a sense. So we have a subspace V, and a set of vectors that are linearly independent and spans the subspace is called a basis. So it could be that we potentially have two different sets of linearly independent, or actually multiple sets of linearly independent vectors that span the same subspace. But it also turns out that they can have different cardinality. Okay, so they can have a different basis. So this subspace has two different bases, but the number of elements is the same. So all the bases for a given subspace have the same number. This is a theorem in linear algebra, and that number is called dimension. Dimension of a linear space is the number of linearly independent vectors that spans it, no matter which like subset you pick. As long as they're linearly independent and span, then it would be a basis. Sorry, like a basis, and the number would be dimension. Okay, this common number is called. Question? Was it fast? Slow? Okay. Some people are like this. Majority are still not warmed up. Is it okay? Any questions? I'm going to pause a little bit. If you are on board. How many different possible bases a subspace can have? Anyone? 2, 3, 4. 5. How many bases a subspace, like a linear subspace, has? Anyone? Maybe I'll come back to this. How many bases like a linear subspace can have? So in this example, the dimension is 2. Just think about that question in the background. So the dimension kind of formalizes this notion of degrees of freedom. So you have 2 degrees of freedom if you are on the xy plane. Right, so if you're on the plane, okay. If you're on a plane there are two directions that you can go. I mean, it could be these two directions or these two directions, two independent directions. If you're on a line, there's just like really a single independent direction. So it's like a notion of degrees of freedom. One way to formalize it in math is via the notion of dimension. Okay. So how many bases the subspace can have? Yes. Yeah, infinitely many. Yeah, infinitely many. There's no like fixed number. The number of elements is always the same, but the bases themselves are infinitely many. There's no reason why you necessarily would pick this. This is easy for us to work with, but this is like good. And then the easiest way to see is in this case, for example, I can just multiply this vector by like 2 or 3 or any real number. And they just multiply one of them by any number. Yeah. And you can make it more complicated as well. Okay, so although there are many bases, but that's not going to be a problem for linear algebra. Okay. Next topic. Any questions so far? So now we're going to look at the matrix. Okay, so far we've seen sets of vectors. The easiest way to think of a matrix maybe is just I'm going to put these vectors into the columns of X. So you had a bunch of vectors, x1, x2, xn. So a natural way to view this set, this is a set of vectors, is as a matrix, which is hopefully you know like it's just an array of numbers. And in our, let's say RD, so I'm going to put them in the columns. So this side would be d-dimensional, and then I have n of them. So for example, you have like 1, 1, and then 1 minus 1. I can form a matrix like 1, 1, and then 1 minus 1. I'm going to put it in the rows, but we're going to focus on the columns because that's like nicer to do regression. So the n and d are going to be like switched when we go to regression. So if we view a matrix as a set of its columns, then we can talk about the span of this set of vectors. So if you look at the matrix, yeah, it has a bunch of columns. You look at it as a set of vectors. So these set of vectors will have a span. Okay, that span is a subspace, and that's called the column space of vectors. Okay. Let's see if that comes up. Okay, we have P actually here. That's a little bit better. So P. So this dimension is going to be P. Let's say they're in Rn. So each one is in Rn. So Xi is in Rn. So this is going to be n. So to match with what we'll see later. So it's going to be, so I have a bunch of vectors in Rn. So this is the notation. This subset of vectors is Rn. And then I have P of them. And then I form a matrix out of the columns of like a matrix whose columns are these vectors. And then I'm going to look at the span. So the span of these vectors is the set of all linear combinations. Okay. So that's called the column space. Here we're going to just notice that this linear combination, let me mention this. So span, so column space of X is just going to be the span of X1 up to XP. So you look at the columns and you look at them as a set of vectors, and they have a particular span. It's a subspace that's called the column space of X. Some people might write it as the image of X or range of X, whichever you like. And But the definition of a span is the set of all linear combinations. So you would write it as the set of all, it could be C, it could be beta, it could be any scalar here, that doesn't matter. So this is a scalar times xj, and j goes from 1 to p as beta 1 up to beta p vary in R, okay? So when I form a general linear combination, it doesn't matter what I call the coefficients, they're dummy variables. It could be Ci, beta I, or beta j's. I can use them in extreme if I want. So that's the way that you can write the column span. So the column span or column space of a matrix is the set of linear combinations of the columns, and the linear combinations look like this. The thing is worth noting is that this can be compactly written as a vector product. Okay, so if you form a vector out of these coefficients, you get a p by 1 vector. Okay, and this is n by p. So I have an n by p matrix and a p by 1 matrix. So the dimensions of matrices need to be compatible for matrix product, and in this case, they are, so the inner dimensions match. So I can multiply this matrix by this matrix, which happens to be also the vector. What will be the dimension of the output? N by p by 1. Yes, n by 1. People remember matrix product, matrix vector product. How do you multiply a matrix and a vector? Suppose I give you 1, 1, 1, negative 1, and a beta 1, beta 2. How do you multiply them? Like this. Maybe say it. Like, anyone? I just want to see how you multiply it. Maybe someone new who hasn't talked before. This should be easy if you remember matrix multiplication. Yes.
You go row by column, dot products.
Row by column. Yes. So the first row times the first column. And if there was another column, then, so this would be just the first element, right? So dot product of this and that are basically 1 times beta 1 plus 1 times beta 2. So I get beta 1 plus beta 2. And then the first row times the second column, which doesn't exist, would be here, and so on. And then I go the second row, right? Okay. Second row times, you start to multiply by the columns, right? So the second row times the first column would be beta 1 plus beta 2, and that's all we have. The first row times the first column, first row times the second column, first row times the third column, so that would be the first row. And then you go to the second row, you just multiply dot product with each column. Is that how you remember? Okay. So let's say 1, 1, 1 minus 1. And then you have beta 1, beta 2, C1, C2. So what is this element? How do you find it? Yes, how do you define it? Who was that? You.
Second row.
Second row.
Wait, and we just gotta use each entry to multiply to each entry on the second column.
Yes, so this is like a second row and then the second column. So you pick the second row here and the second column here, and then you just component-wise multiply and then add. So 1 times C1 and then minus 1 times C2, and just add them up. C1 times 1 plus -1 times C1. Okay, that's not correct. C1 minus C2, okay? If you want to find the ith row and the jth element, we just look at the ith row here and the jth element, take the inner product. We'll see it. Is that how you see, like how you saw it? Is there any other way that you've seen it? No? So this is fine. There's another way of looking at it, which is easier for us, is if I just want to get one column, I can multiply column 1. You can look at the columns of this. And so basically the first column, or whatever column I want, so this column is going to be a linear combination of the columns of this, with the coefficient determined by this column. Okay, so this column would be beta 1, 1, 1, plus beta 2, 1 minus 1. So if I want to determine the first column, I look at the first column here, and then the coefficients would be coefficients in a linear combination of the columns. So this view is very useful for us. Now, for example, in this case, for this column, it would be, I'm going to look at this column. These would form, give me the linear combination coefficient. So we're saying the column. So this column would be C1, 1, 1, plus C2, 1, -1. If you haven't seen it, and try to think about it, this gives you, for example, C1 plus C2 would go here, and C1 minus C2 would go here. Okay, so you can think of the columns of the result as linear combination of the columns of this side with coefficients given by the columns of the second B. In particular, if you just have a vector, right, there's just one column that you produce because there's just one column here. So there's just going to be one column in the output, and that column would be just a linear combination of the two elements. Okay. The two vectors. Okay, did that go as planned? Does this make sense? Very useful fact. And if you understand this, then you'd see that if you have an x beta, and the columns are x1 up to xp, and if I multiply by a single column of coefficients, then I just produce a single column, which is a linear combination of these. So beta 1, x1 plus beta 2, x2, beta p, xp. Okay. So matrix vector product is just generating these linear combinations. Okay, that's another way of it. How's going? Has anyone seen this? Okay, some people have seen. But so this view is very useful for us in regression. So, any questions? So if you now look at the column span, which is the span of these, which is the set of linear combinations, I can compactly write it as x beta and beta varies in Rp. Okay, as beta varies in Rp, these vectors that are like x times beta, the span, the subspace, the linear subspace, which we call the column space of x, or the image of x, or range of x. Okay, it's a very important subspace, it's a linear subspace. In particular, it will have a basis or multiple bases, and it will have a dimension. And that dimension has a name. And I want to see if anyone remembers what is the dimension of this called. The dimension of the column span of a matrix.
Rank.
Rank. So that would be the rank of the matrix. So this matrix has a rank, which is really the dimension of the column space. in fact, there's a row of space as well, so you can look at the linear combination of the rows. That would span a subspace. So this is a subspace in Rn because these vectors xj's are in Rn. Remember. So the column space is really a subspace of Rn. There's a row space, which is this span of the rows. Because the rows live in Rp, that would be a subspace of Rp, and that would have a dimension. And that turns out that that dimension is also the same as this dimension. So there's a single dimension associated with row and column spaces. That's called the rank. We're going to focus on the column space, but there's just sometimes people call this column rank, and then there's a row rank. But it turns out that the fact of linear algebra, the two numbers are the same. Anyway, so this is called the rank. So column space is also called range. Or image, I might use image, I might use this notation. The functional analysis notation, maybe I'll talk about this later, but you can view X as an operator that moves vectors from Rp. So if you give me a vector in Rp, X beta produces a vector in Rn. Okay, it's like a machine that transforms vectors from one space to another. This is called an operator. So you give me, like this is an operator. It takes beta and maps it to X beta. This is a vector in Rp, and this is a vector in Rn. It's called an operator. It turns out to be a linear operator. And I'm not gonna dwell on what a linear operator is, but it's like a function. It's a function that maps from one space to another. And this is basically the image of the entire Rp under that map. So the entire Rp maps to some subset in Rn, which is that column space. That's by definition. All the vectors that you can get out of X beta is column space, so you can think of it as the image under a map. And this is like the functional analytic view. So a linear operator. The matrix is a linear operator. And column space of X is really image of Rp, or the input space under this operator or map. We're not going to use this much, but it's much more beautiful view of matrices. They're like operators. They operate on vectors, produce vectors in other vector, another space. Okay. So the rank is the dimension of the column space, and then like image, as I'm going to write it, and so compact means dimension of the image. Question? Another way of saying it is the rank of X is the number of linearly independent columns of X. Okay, because the entire set of columns of X would span the column space, but not all the columns go. If you look at all the columns together, they might not be linearly independent. So for example, if I have this matrix, hopefully by now you see that the two columns are linearly dependent. So the span of them is really one-dimensional. So image of this matrix is really a span of these two, which we can write also as the span of this, and this happens to be a set of linearly independent vectors. So I can conclude, if I call this X, I can conclude that the rank of X is equal to what? 1. Yes. So the rank is not the number of columns, but it's actually, you can think about it, it's the number of linearly independent columns. Because I mean, all the columns span the thing, but not all of them are needed. You just have to find the minimal subset that spans the Well, because that's the definition of dimension. Remember, the dimension is a set of linearly independent vectors that span the same subspace. It's not just enough to span; they have to also be linearly independent. So I can look for a subset of the columns that are linearly independent and span the whole thing. It's not enough to be linearly independent, and it's not enough to be spanning. They have to have both properties. And then if I find that set of columns, then the rank of the matrix would be the number of those columns. This was comes from the definition of combining the definition of dimension with what the definition of an image or column space is. Okay. This rank probably is like maybe a confusing concept when you first look at it, but once you get used to it, it's really not something difficult to grasp. Questions? How many of you have seen rank before? Rank of a matrix? Okay. I'm assuming that most of you have seen if you've seen linear algebra. Okay. This time we're going to move on. If you have questions, let me know. There's another subspace associated with the matrix. So there's the image or column space. There's another interesting subspace which is called the kernel. And so the kernel, we look at these linear combinations and look for betas that make this linear combination equal 0. Okay, it's a set of betas. So again, remember X is in R. This is my notation for the matrix that has dimension n by p and whose values are like real value. So it's a matrix n by p. And so if I multiply it by, this is X, if I multiply it by beta, beta would be, in this case, would be n by 1. Actually, it would be p by 1. Sorry. So it has to be p. So this dimension has to match this side. So this is p by 1. And so the result would be, this is actually not a good AF. So this has to be small, should match this. This is going to be p by 1. And so I would have a vector here, which is n by 1, and I want it to be perfectly 0. If I find a beta that looks like that, it's a beta that witnesses the fact that the columns of X are not linearly independent. Because this is a general linear combination. If I find a beta that's non-zero, I mean, 0 is always satisfying this, so 0 is always in the kernel. But if I find another non-zero vector, then it's more interesting because then it's a like non-trivial linear combination that I can say equal to 0. And so it's basically the set of all linear combinations, like coefficients of linear combinations that witness the fact that the columns are not linearly independent. So 0 is always in the kernel. So it could be like the kernel is just this. If the columns are linearly independent, the only vector that can work there is 0. So the kernel would be very simple. So if this happens to be the case, only 0 works, then I know that the columns of X are linearly independent. It's like, right. But if there are other vectors in there that are non-zero, then those would form a linear combination that's not trivial and is equal to 0. So its kernel kind of captures that. The vectors, or if you look at it as a linear operator, it's the set of vectors in Rp that maps to 0 to the other side. So it's a subset of the input space. So again, if you look at it as a linear operator, X maps vectors in Rp, like beta, to vectors in Rn, like X beta. And it's a subset of the input space of X, like the domain of X, that is mapped completely to 0. So it could be like the entire line. So let's say this might be R3. It could be that this entire line gets mapped to the origin here. Maybe this side is like n is 2. this whole thing might be mapped to 0. All the vectors here just map by x to 0. And that's the only set of vectors in R2 that map to 0. So this would be the kernel of x. So the kernel of x, as well as the image, are linear subspaces. So in R3, for example, there can be lines and planes that pass through the origin. And so that's the definition. Okay. Have people seen the kernel? Yes. So these are the two interesting subspaces. One is associated with the input domain. So that's the kernel. One is associated with the output, is the image. So the set of all vectors. So the image is basically the set of all vectors that you get as you map everything here. The kernel is the set of vectors here that are mapped to 0. It's a little bit like dual in a sense. So let's see if people understand what is the kernel of this matrix. Actually, what is the image? The image we already talked about. So the image is the span of these two. So the image is just a line. Let's see what the kernel is. Dimension is 1. So what is the kernel? So the kernel is a little tricky. So I have to write this down. So beta, I have to pick a general beta, like beta 1 and beta 2, because we have two columns. And then I form a general linear combination of columns, that's x beta. And then I set it equal to 0. And if you look at it, you get two equations, but they're basically the same equation. So you really get one equation. Okay, so this is like a mathematical description of it. The set of all vectors are 2 such that they satisfy this equation. Okay. So what is the set? What does it simplify? It's a particular line that passes through the origin. And I can talk about the dimension of this as well. In this case, what is the dimension? Dimension 2 would be a little bit optimistic because 2 is the entire input space, so it's the maximum. If dimension of the kernel is 2 in this case, it means that it just maps all the vectors to 0. And the only one that can do that is just a 0 vector. So the other one, get 1. The two other options, 1 or 0. So this one would be 0. So you could have the dimension of the space, and you leave is 0. Let me check. This is one of 3,000 questions. Math, like in your algebra. What is the dimension of that subspace? Right. Dimension is here going to be 1 because this is like intuitively in R2, this is a line. But if you want to prove it, you have to show that I can write everything here as like a scale multiple of like some vector. That's not obvious, but you might try to do it like find a vector that satisfies this. So can you give me a vector that satisfies this equation? Let's say beta 1 is 1. What should beta 2 be? Would that work? So this is one vector that's in the kernel. And you can argue that anything that looks like this would be a scale multiple of that vector. Then you put in the kernel is like has dimension 1. This is not maybe obvious, but a little bit of arguing, mathematical arguing would show that the set of all vectors that look like this is the same as the set of all vectors beta 1 beta. But intuitively, you can see if you plot this, you've probably seen it from like elementary, like high school. Like this is a line. Anyways, this is sometimes called nullity. So nullity is the rank of the kernel. rank is the, no, sorry, nullity is the dimension of the kernel, rank is the dimension of the image. And it turns out that there's a relation. So the rank of X plus the nullity of X turns out to be one of the dimensions. In this case, it would be like this dimension. So they add up to um, 2. In this case, you can see 2. We'll hopefully see a result that makes sense of this. You don't have to remember it. But once you lose a little bit of image, you add a little bit to the kernel. Okay. Okay, we're done basically for today. Next time we're gonna do the, so any question? Oh, it's fast, but yeah, 2 minutes. You're not done yet.
Are you able to post your iPad notes?
Yes. Once the website is up, then you'll have like a box folder there, and I'm gonna post these on the box folder. There's no question. People are happy to read it. Okay. Okay, next time we'll talk about inner products. Thank you.
Regarding the exams.
Give me a second. Yeah.
So.